All right, welcome everyone to the short poster spotlight session. My name is Jakob Runge. Welcome everyone. And I kindly asked the speakers to come down to the stage, to the side here, which would be Phillip Lippe, Thomas Walsh, Florian Kalinke, Stefan Radev, Jakob M. Chen, Jiajing Li, I hope to pronounce it correctly, Pierre Glaser, and Chuqing Zhu. I hope everybody is in person. That was the information I got. So as you know, the session is fast paced. It's just 20 minutes that we have. And we will try to do that as quickly as possible. So we have 20 minutes divided by 8, and it's 2 minutes, not 2.5, as some of you might think. And I need to be a bit harsh on keeping the time, but I have a nice, cute old timer, as you will hear. So without much further ado, I would like to get the slides online and then ask Phillip Lippe.
Thanks. Yeah, I'm Phillip. I want to give you like a quick teaser of our method, BISCUIT, causal representation learning from binary interactions. BISCUIT is essentially a method to learn causal variables of interactive environments, which you only observe by high-dimensional data, such as images. As an example here, you have an agent that can interact with an embodied AI environment, such as here a kitchen. By low-level actions, like you can assume, you have a robotic arm that can interact here with different objects. Our goal is to go from such videos to basically a causal graph of what different objects and causal variables are in this environment and how they interact. How we do it is essentially that you have a VAE-based architecture which maps images into latent space in which you disentangle the causal variables. And to encourage this disentanglement, we basically assume that the action here can be described as essentially switching between observational and interventional mechanisms for these different causal variables. In the paper, we also show theoretical results, how you can actually prove that this can give you the ground truth causal variables. Once you have identified the causal variables, what can you do with them? Well, you can now, for instance, simulate latent interventions. You can, for instance, take an image and say, how would this image look like if I would turn off the microwave? This you can now do quite easily once you have them, because you can simply swap out a latent variable with another one of a second image, and therefore also create actually novel combinations of causal variables that you have never seen before. If you're interested in learning more, come by our poster, also check out our project website. Thank you.
Okay, hi, I'm Tom Walsh. I'm from Sony AI. I'll be talking about composing efficient, robust tests for policy selection with my co-authors at Sony AI. So this paper is born out of a real production problem. Back in February, Sony AI deployed reinforcement learning trained agents into the game Gran Turismo 7 on the PlayStation, and 200,000 unique users raced against our policies. If you're going to do something like that, you can't just have a nice learning curve. You have to pick a single policy to go send out into a deployment. And this paper is about how you build a small set of test cases to figure out which policy to send. It's a non-trivial problem because you may have hundreds of policies from all your learning runs, and you may also have hundreds of test cases. In our setting, every straightaway, every curve, a curve with a car in front of you, a curve with a car behind you, a curve with a crazy car next to you. Those are all test cases, and they're all going to happen in the real world. But you can't run every test case on every policy. And in addition, this is UAI. We have uncertainty over the future policies we might have to test and which test cases might be the most important. So luckily, we have a robust solution to that uncertainty. It's called Riposte. It's an algorithm that starts with a data set from a small set of tuning policies run on all the test cases and turns that test set, data set into a two-player zero-sum game with an antagonist that picks the uncertainty parameters and a protagonist that has to pick a small set of test cases to minimize error against using the whole test set. We use that to pick policies for bimatrix games, poker playing agents, and agents to race in Gran Turismo 7. So if you're interested in diagnostic testing, how to deploy real-world reinforcement learning agents, or if you just like fast race cars, come to our poster number 257. Thank you.
Okay, so happy to share our spotlight presentation of our article Nyström M. Hilbert-Schmidt independence criterion. I'm Florian Kalinke from KIT in Karlsruhe, and this is joint work with Zoltán Szabó from London School of Economics. And we are working on dependency estimation. And specifically, we use what's called a Hilbert-Schmidt independence criterion in the machine learning community. But I think in the statistics community, people call it the distance covariance, which is precisely the same notion. And this is a very popular dependency measure and has multiple applications. People use it for causal discovery, for feature selection, for biomarker detection, for really a lot of things. But the main bottleneck is the quadratic runtime. And there exist speedups, but these existing speedups are limited to 2 random variables. So we call them components because it's a bit more general, and they have no guarantees. So the contributions that we do allow speedup for more than 2 random variables, and they improve the runtime from the quadratic runtime to n to the power of 3/2. And we prove that the convergence rate is 1/√of n, which is precisely the same as for the quadratic time estimate. We also perform some experiments, for example, for causal discovery, dependency testing of media annotations, and also on synthetic data. So if you're interested in applying this general dependency estimator, please drop by our poster. And also if you're interested in the mathematics on, yes, we can have a chat about this. The number is 294. Thank you.
Hi, everyone. So I'm here to advertise our JANA framework for amortized Bayesian inference. So amortized Bayesian inference attempts to scale Bayesian inference to complex models, which are typically intractable with standard methods, such as Markov chain Monte Carlo or sequential Monte Carlo. And of course, as usual, the most challenging part of this work was to come up with the acronym. So now, how this works, we use 3 neural networks. Take any parametric Bayesian model, which we can use to simulate data and parameters. And we have these networks. A summary network learns informative embeddings of various data structures. A posterior network learns amortized posterior, and a likelihood network learns to amortize an intractable likelihood function. And on their own, these 3 networks can already do cool things, such as misspecification detection and various estimation tasks. Together, they can even do more cooler things, such as marginal likelihood estimation or posterior predictive estimation, which are typically doubly intractable in Bayesian inference. And so if you're interested in Bayesian inference, just come to the poster and we can talk about how we validate such networks and what kind of experiments we did and how we benchmark these networks. Thank you.
Hi, everyone. My name is Jakob Chen, and today I'll be talking to you about our work with causal inference with outcome-dependent missingness and self-censoring. This is joint work with Dan Malinsky and Rohit Bhattacharya. So let's say you have an observational study where the outcome is self-censoring, and our target parameter here is the average causal effect. And as you can see in figure 1, we have a confounding bias from observed covariates W and unobserved covariates U. And we also have self-censoring on the outcome. And self-censoring just means that we have a situation where a variable causes its own missingness. So for example, if I'm trying to evaluate the smoking proportion on a college campus and I just send out surveys asking people if they smoke, those who do smoke are less likely to be willing to respond to my survey. So if I only consider observed rows of data where individuals do respond to my survey, then I'll have like an undercount of the true smoking status on a college campus. So the 2 main contributions of our work is we have an identification result for the average causal effect by using backdoor adjustment to adjust for a confounding bias, and shadow variables from Miao et al. 2015 to adjust for the self-censoring missing data bias. And the second contribution here is we have empirical tests to identify when you're able to use our identification strategy as long as you have an incentive variable I, and that's just any variable that affects whether individuals are willing to respond to our survey. So for example, giving Amazon gift cards so that people are more willing to respond. And here's our identification result. We use an inverse probability weighted estimator where we reweight by the probability of response to the outcome and also the probability of receiving the treatment A. And the empirical tests for identifying conditions also use only observed data. So if this is interesting to you, then please come by my poster this afternoon and we can chat. Thank you.
Hello, everyone. I'm Jiajing Li from the King's College London. So the current PLM-based text classifiers tend to overestimate the predictive confidence when making false predictions. So as shown in this example, a BERT classifier trained on the Go emotion state side when given a high confident prediction on the wrong label disappointment rather than the correct label disapproval. So in the current paradigm of the NLP research, the base model is an over-parameterized network usually pre-trained on the large-scale data with different training objectives, such as predicting the missing token, which are different from the downstream tasks. To this end, the epistemic uncertainty is from the model, and the aleatoric uncertainty is from the data distribution. So in our work, we tend to estimate and interpret the source of the uncertainty on PLM-based classifiers. Firstly, we decompose the mean squared error to aleatoric uncertainty and epistemic uncertainty. Since we assume the true label distribution follows the Gaussian distribution, to decrease the epistemic uncertainty, we want to increase the true predictive variance. So we propose to map the input representations for latent space and manipulate the latent code, leads to the resulting label distribution closer to a uniform distribution in the out-of-distribution area. So after plugged in the Q, the perturbed representation can reduce the overestimated predictive confidence. And by examining the difference between the text representations, a subset of the input features, which are the word tokens, can be identified as the interpretation of the original model's predictive uncertainty. Thank you, and welcome to discuss during the post-session 3.
Hello, so I'm here and I'm quite excited to talk about my work at UAI today, which is about kernel-based tests for testing calibration. This is joint work with my awesome collaborator, David, Phillip, and Arthur Gretton, my supervisor. Oh, sorry. So our object of study are probabilistic models, probabilistic predictive models, in the sense that given an input y, given an input x, this model will try to predict a certain output y and will return a set of possible outcomes, which are all associated with a specific confidence score. And those confidence score make up a probability distribution, which is not necessarily an approximation of the conditional distribution of y given x, but actually also incorporates uncertainty coming from expectation, imperfection in the data or in the model structure itself. And in that setting, Q is said to be calibrated if the condition on the fact that the model outputs a specific probability distribution, so a specific set of confidence scores, the output indeed on average is distributed according to this confidence score. And so this property captures the fact that the uncertainty input by the model is trustworthy, honest, or reliable. In that setting, it might be obvious to you, but calibration test seeks to find any form of miscalibration in a data set when you're giving a probabilistic model associated to it. And that will be the object of this paper, finding good calibration tests. So right now, we're going to make just one last assumption, which is that the output is actually continuously valued, which is the primary use case of interest in Bayesian inference, which is where I come from. And for this, currently available method requires expectation oracles with respect to the probabilistic model, which is not realistic when the model is unnormalized. This requires actually approximations like MCMC, and this approximation has a negative effect on theoretical guarantees like type 1 error controls, and also make the test very, very slow. Our contribution is to propose a new test that doesn't require any form of MCMC approximation. And thanks to that, is fast, theoretically grounded, controls its type 1 error, and also is able to detect any form of miscalibration alternatives. Thank you very much.
Hi, everyone. My name is Yuqing. This is a joint work with Xuandong, Chuan, and Yuxiang. This talk. Okay. This talk is about private predictions. In this problem, we consider a prediction interface that has access to a private label dataset. As the goal is to make predictions on a sequence of unlabeled queries Q1 to Qt while preserving privacy to your training set S. And we use differential privacy to measure the privacy loss, which is a quantifiable definition of privacy loss and has been widely used. Existing work on these problems, like they had to account privacy for every individual data point in S, and their privacy loss will grow linearly with a length of t. Thus, they cannot able to answer like they cannot answer thousands of queries. And our method addresses these issues by using a new DP technique that ensures that only a subset of private data points has to pay for privacy loss. I'm giving you an overview here. This is based on kernelized nearest neighbors. For each unlabeled query QI, we will leverage a public foundation model, for example, the feature transformer, to extract features for both your private label data point and your unlabeled query QI. Then we will search neighbors in their feature space and found nearest neighbors whose kernel distance in their feature space is below some threshold, is above some threshold. And then we will leverage those native neighbors labels to make predictions, which is why I tilde here. And our algorithm features like only selected neighbors will pay for privacy loss. And for those unselected data points in your private data set, their privacy loss is always 0. So that's how we improve the utility. And our algorithms also is consistent with other privacy notions, those, for example, machine learning, where user has the right to request a delete of their data points. For more information, please come to our poster.
All right, congratulations again to all speakers. I think they cover a broad range of topics at UAI, and you all got curious and had a lot of questions to be asked at the poster session. But now it's lunchtime, and I think see you again at 2 p.m. here.